Hi everyone, we are presenting our work on improving visual grounding in remote sensing. We propose 2 new grounding pipelines and an assembly boarding strategy that consistently outperforms individual models across 2 benchmarks. Remote sensing imagery is fundamental to applications like urban planning, disaster response, and environmental monitoring. A key capability we want to enable is visual grounding, which is localizing an object in a satellite image given a natural language description. But this is particularly hard in remote sensing due to cluttered scenes, extreme scale variation, and many visually similar objects appearing together. No single model today handles all of these well. Let's look at why. RemoteSAM is specialized for remote sensing and does well at coarse localization, but its predictions are often fragmented or noisy. SAM3 produces excellent segmentation masks, but struggles to find the right object in a large scene when given only the text prompt. EarthMind and Falcon are strong vision language models, but remain inconsistent across diverse object categories. The key insight here is that these models fail in different ways, and that actually is an opportunity. Our work makes 3 main contributions. First, we propose sequential grounding refinement, or SGR, a simple 2-stage pipeline pairing RemoteSAM's localization with SAM3 segmentation. Second, we propose Cluster-Aware Grounding Refinement, or CGR, which is a more principled approach using clustering to fix RemoteSAM's fragmentation problem. Third, we introduce a majority voting ensemble that aggregates predictions across 6 pipelines for maximum robustness. We evaluate everything on 2 datasets, VRSBench and NWPU VHR10. Our first pipeline is SGR. SGR works in 3 steps. First, we use Qwen3 with 8 billion parameters to rewrite the user's query into 2 specialized prompts. One for RemoteSAM that keeps spatial cues on, like on the left side, and one for SAM3 that strips these cues and keeps only the object category, like the yellow car. RemoteSAM then produces oriented bounding boxes as coarse coordinates. Each one of these crops is passed to SAM3, which refines them into high-quality segmentation masks. The final output boxes are derived from those masks. But SGR has a key weakness. When RemoteSAM produces fragmented or overlapping boxes, SAM3 has to process each one separately, often producing redundant results. CGR addresses this by not using RemoteSAM's boxes at all. Instead, we take the raw segmentation logit mask from RemoteSAM, which has a dense pixel level information, and apply dbScan clustering to group related pixels into coherent regions. Each cluster is then cropped with padded and passed to SAM3. We then select the SAM3 mask with the highest IOU to the original cluster pixels as the final prediction.
For the ensemble stage, we execute all 6 pipelines independently, namely RemoteSAM, SAM3, EarthMind, Falcon, SGR, and CGR. Each pipeline produces its own set of grounded object predictions for the given query. Instead of directly merging these heterogeneous outputs, we evaluate how consistent each pipeline is with the others. To do this, we compute an agreement score for each pipeline. The agreement is primarily based on the intersection over union, or IOU, between predicted bounding boxes across different pipelines. In addition, we introduce an exponential penalty term when there are large discrepancies in the number of detected objects, so that pipelines with inconsistent object counts are weighted less favorably. After computing pairwise agreements, we aggregate the scores for each pipeline to measure its overall consensus with the ensemble. The pipeline with the highest aggregate agreement score is then selected, and its predictions are used as the final output. This strategy allows us to leverage the complementary strength of multiple grounding approaches while avoiding the complexity and instability that can arise from directly fusing segmentation masks or bounding boxes from different models. In practice, it provides a simple yet robust consensus-based mechanism for improving overall grounding reliability. We evaluate our methods on 2 remote sensing benchmarks. The first is VRSBench dataset, which contains over 29,000 images and more than 52,000 annotations. The dataset also includes semi-automatic verification, making it suitable for large-scale grounding evaluation. The second dataset is NWPU VHR10, which contains 8,800 high-resolution aerial images across 10 object categories, with spatial resolutions ranging from 0.2 to 1 meters. For evaluation, we primarily use intersection over union or IOU to measure grounding reality. The IOU computes overlap between predicted region and the ground truth region divided by their union. A higher IOU indicates a better localization accuracy. We also report the mean IOU, which averages the IOU values across all evaluation samples. This provides an overall measure of grounding performance across the dataset. On the hyperparameter side, the CGR pipeline uses dbScan clustering with epsilon equal to 20 and a minimum cluster size of 5 samples. After clustering, the regions are padded with 10% before being refined using SAM3 segmentation. For the ensemble and mask selection stage, the final cluster mask is selected based on the region with the maximum IOU with cluster pixels. We also apply a count-based penalty term of the form exponential of minus lambda times the absolute count difference, where lambda is set to 0.5. This helps penalize inconsistent object counts across different pipeline predictions and improves ensemble robustness. Here are the quantitative comparison of all evaluated methods across two benchmark datasets, VRSBench and NWPU VHR10. Starting with the baseline models, RemoteSAM achieves a strong and consistent performance across both datasets, particularly VRSBench. Falcon also performs competitively, especially at higher IOU threshold of 0.7, indicating relatively precise localization. In contrast, SAM3 alone shows weaker performance on VRSBench, which highlights the difficulty of directly applying segmentation-focused models to complex grounding tasks without additional refinement. Moving to our proposed methods, both SGR and CGR demonstrate the benefit of multi-stage refinement. CGR consistently outperforms SGR across almost all metrics, showing that the cluster-aware refinement strategy improves localization, robustness, and object consistency. The best overall results are obtained by the majority voting. On VRSBench, it achieves the highest IOU of 0.645 and the best accuracy at 0.5 and a threshold of 0.792. Similarly, on NWPU VHR10, the ensemble reaches a mean IOU of 0.603 and the highest accuracy values across both thresholds. These results demonstrate two key observations. First, different grounding pipelines exhibit complementary strength. Second, the consensus-based ensemble effectively leverages these strengths to produce more reliable and accurate grounding predictions than any single model alone. Here are some key observations from our experiments, along with current limitations of our proposed framework. Starting with model behavior, we observed that different grounding pipelines exhibit complementary strengths and weaknesses. RemoteSAM provides reliable coarse localization and generally identifies the correct object regions, but its outputs can sometimes be fragmented, especially in cluttered scenes. On the other hand, SAM3 produces high-quality segmentation masks with cleaner boundaries, but it often struggles with accurate object localization in large-scale remote sensing imagery, where multiple visually similar objects are present. We have already discussed how our proposed pipelines and the majority voting scheme give us better outputs than the single models. However, we have also identified some limitations. The current ensemble setup is somewhat biased towards RemoteSAM because it is present in multiple derived pipelines, such as SGR and CGR. As a result, the consensus process can favor predictions that are closer to the RemoteSAM outputs. For further work, we plan to include more independent grounding models to improve diversity within the ensemble. We also aim to explore weighted voting and confidence-aware aggregation strategies, which could provide a better balance between localization accuracy and segmentation quality while making the framework more robust across diverse remote sensing scenarios.